Hello, this is John. Right now we are going to talk about the Viterbi algorithm, which is an algorithm that you use off of hidden Markov models. So a hidden Markov model, if you didn't know, is a Markov model, but the states are something that you can't observe. So a good example would be like somebody's mood is their hidden states, but the output would be some behavior like the color of shirt they wear or something like that. So in this case, we have two states, sunny and rainy here, and then we have two outputs. The outputs are whether somebody from that city reported a lost passport or whether no passports were reported lost that day. So in this example comes from the book, and it said that there's a manager who gets reports from both London and Athens, and he thinks that he can predict the weather in those two cities based on the reports of lost passports. So the first example they give is where he gets an output from London of 3 days no lost passports, but the last day, the fourth day, somebody lost a passport. So what we do with that is we're going to use that in a minute. Let me finish explaining these tables here. Okay, look at this a little bit more closely. All right, so the hidden states, the guy doesn't know what the weather is in London, but he knows the probability that it will change from one state to the other. That's this first table right here. So this is called the transition states. So sunny to sunny, sunny to rainy, and so forth. The next two on here are the output probability. So these two here. So this one up top is saying that if it is sunny, it has a 70% chance of somebody losing a passport for that day. And that is this table right here. Okay, so now that we have that set up, we can use this output, this one, to predict the weather. So I will just show you the first one because it's pretty tedious, but you make one of these calculations, you can do the entire chain and figure it out pretty easily. But the pattern is this. We're going to keep track of a few variables. This one is called the sunny score. This one is called the rainy score. And that is going to be fed along these rungs here. Each row is a state. So I got sunny right here and the rainy on the bottom. So this sunny score here is going to start in this rung and be updated as we move down the lattice. Same thing for the rainy. Alright, so what we're going to do first is calculate this transition here from sunny to sunny, given that we know nobody lost a passport on that day. So it's going to look like this. We use this formula right here, which is basically saying the state that you're on, the previous state, and then that's times. This side is, what is this going to be? The state that you're in, and I guess that's on this side, and the output. So those are our pairs for these terms in this first example. So what you got ultimately is you need to test both of these legs here. This one, we're going to test that one, and this one, and see which one is higher. So S score times sunny to sunny from the first table, which is 0.75, and then sunny with an output of no passports lost, which is 0.03. Change color. Alright, so we got the starting state score the probability it's going to remain sunny, and the probability that there is going to be no passports missing for that day. And that gives us this number here, 0.12. So you keep track of that. Then you do the same thing for the rainy probability. So that's this guy. We're going to start with the rainy score, 0.45. And again, that is coming from this starting state right there. We're assuming that the day before this state was rainy. That's represented by that line right there. Alright, so rainy to sunny. Notice how this one was sunny to sunny. Then down here, rainy to sunny, which I will look up real quick. Well, actually, I have it right here. It's 0.03. Excuse me. Okay, and then the next one, B, is rainy with an output of no passports lost. So if we look at the table, that is 0.8 because everyone is inside. Alright, so once again, a rainy score times the probability that it will go from rainy to sunny times the probability that nobody will lose a passport on a rainy day. And that gives us this number here. So to update our sunny score, we're trying to get a value for this right here. We are going to see which one out of these two values that we just calculated is out of these two values, which one is higher. So that's max of the sunny versus the rainy. Obviously sunny wins out. That is why there is a bold arrow right here, because we basically dropped this. Excuse me for not pointing when I should be. We bolded this arrow because that's we're going to keep that connection. This one we dropped, the one in red. Okay, so then once you did those two connections, you got to do the other two, which are this one and this one, which I'm not going to do again because I have another example to do this with. But basically, we calculate all of these scores for the lattice. Each time we're keeping track of which one was the winner, and we get this lattice here. Oops, that's not with these connections. And what this is saying is that if you had this output, you can trace it back using those connections like this. Okay, and I think what this is saying is that the most probable weather for that day, or for that output, was that it was rainy, 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 sunny, and sunny. Possibly. Maybe that last one doesn't play into it, but I think it does actually. Rainy. Okay, so the problem in the at the end of the chapter extends this same setup, and it asks you about Athens. So I did that a little bit further down. So I took the Athens model. It's got different probabilities for each transition and each output, and those are these two tables again. So this is your transition, your A table, and B table for the output. Okay, I brought the same lattice down, and I did not verify if I got the right answer, so if I got it wrong, it could give somebody an opportunity to make a correction. But what I came up with is that the most probable transition, let's see, was starting here, 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 and here. So I think that given this output from Athens, the weather would be something like sunny, 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 and then it went rainy. I think that could be wrong. So if I'm wrong, please correct me. But just to reiterate, we did the same thing here. you keep track of these two scores that are running along the lattice, sunny and rainy. And then for each of these pair of transitions to the next state, you consider that score from the previous state. Oops. Right here. Darn. Times the transition from the A table times the output probability. And yeah, so you keep doing that, and then you're left with the transitions that stayed behind to give you a most probable prediction. Thank you for listening.